Welcome to this lesson on performing linear regression in Python using Scikit-Learn. Today we're going to take a look at linear regression in its application, just the concept overall, split the data into training and testing sets, perform linear regression, evaluate the performance, and interpret the results and make some additional predictions. In this lesson, we're just going to review that linear regression is a way to explain the relationship between a dependent variable and one or more explanatory variables using a straight line. So linear regression is used for a continuous outcome variable. In this example, we're going to be finding a relationship between the ticket price and the number of passengers on public transportation. Predictive models in general are used to take known information to develop or train an equation or a model that can be used to predict values for different or new data. Today we're going to focus on the correlation coefficient, which shows the strength and direction of linear relationships between variables. This is the formula used to calculate it. The minus and positive signs tell us what direction the relationship is. If both are going up or down, it's a positive value. If one goes up while the other one goes down, then that's a negative value. And the strength is in how close the value is to either 1 or negative 1. The closer it is to 1 or negative 1 indicates a strong linear relationship between the features. The second item that we're going to look at is the coefficient of determination, and that provides information about the goodness of the fit of the model, how good that model is in describing or predicting the outcome variable. Values that are close to 1 indicate a good model fit, and the values can range from 0 to 1. This is essentially just the square of the correlation coefficient. Another formula that you can use to calculate the coefficient of determination is this one down here below. Today we're going to work inside of Google Colab. It's a great space to work in. You don't have to worry about as many dependencies or creating virtual environments, and so I like working in here. We'll be working with this transit demand linear regression data set that I'll be putting the link in the description for where you can find this data set. And so let's go ahead and start. We're going to start by loading our libraries. And for pandas, SPD, import matplotlib, for plotting, import Seaborn, SSNS, from Scikit-Learn dot model selection. We're going to import the train test split. And what this does is it's going to allow us to be able to take our data, let's say we have 100 samples, and choose a percentage of that data to actually create the equation or our model from, and then test it out on the holdout data. The remaining, let's say, 20% in our case. From Scikit-Learn dot linear model, we're going to import linear regression, and from Scikit-Learn dot metrics. Metrics will allow us to determine how good the fit is. This is where we'll have our coefficient of determination, and also we'll look at the mean square error. I like the prompts that we get here. They allow you to autocomplete, and we're going to R squared. R squared score. Our data set, pd.read, it's a CSV file format. And I've already uploaded it to this workspace, so I'm going to go ahead and copy the path, put the quotations around it, and then just paste it. Let's take a look at the first 5 rows of this data set. Oh, I forgot to run it. Gotta run it first. So we run it, and let's run it again. Okay, so here we go. This is the data set. It has city indicated by numbers 1, 2, 3, 4, 5. number of weekly riders, price per week, population of the city, monthly income, and average parking rates. The number of weekly riders is dependent upon these items here, these features. And so this one is our output or outcome variable. Sometimes it's called a target or ground truth. What we're going to do is take a look at the correlation coefficients and the graphs between, and see how they actually compare to see if there's any linear relationship between any of these features and the outcome variable. We don't have to really worry about city in this case because we're not looking at it as being correlated. You could if you had some more information related to location, but we're going to actually end up like just ignoring this one here. And another thing I did notice when I took a look at this is look at the schema for this one, df.info. The info is going to provide us with the data types, if there's anything missing, and basically how complete the data set is and how much data we have. This is a very small data set. We have only 27 entries of 27 rows. None of them are missing, but this is actually this is incorrect data type. Should be like a string or an object data type. I'm not going to worry about it as much because I'm not going to deal with it in this example. Take up the columns. I like listing the columns, so sometimes it's an easy way to kind of grab the information that you need. So I want to explore the data set by taking a look at just the graph first to see if do we see anything that looks linear. If we put through a straight line through the data, would it make sense to actually use a linear equation for this data? So what we're going to do is take a pair plot, SNS dot pair plot. And I'm going to take the plot of everything except the city. I'm going to use double brackets to indicate like that's the subsets of data frame. And it should be lowercase. PLT.show, so we can see. Okay, and while that's running, I also like to take a look at not just the image, but I also want to see what the number is for the correlations between them, like how strong that correlation is, and we'll do that in the second cell. When you look at the data, you clearly see straight line data. So this is a good data set for doing linear regression. In our case, we're not going to use all of the features. We'll just use one predictor or one input and the output feature. So this will be simple linear regression. Our feature of interest is the number of weekly riders. We want to see how the number of weekly riders stack up against the other features, the other input features. When I look at the average parking rates per month and the number of weekly riders, it's going down, so it means it's a negative slope. In other words, what this means is that this has a negative correlation. So when the average parking rates increase, the number of weekly riders actually goes down. And you might think, well, if the rates for parking increases, wouldn't the ridership go up? But when you look at the second feature, which is monthly income of riders, when the monthly income of riders increases, then the public transportation also decreases. So those two are likely related. Population of a city. If the population is a larger city, you're going to have more public transportation. And when the price of the ticket increases, then that will show a decrease in the number of riders. All right, now that we've taken a look at that, let's take a look at the actual number associated with the correlation. So we're going to go same features. Let's go back and take this. So we don't have to reinvent what we're doing. Let's take this little piece here. And we'll say, hey, this dot core, and get the correlation. And so what we see here, again, we're going to work with the number of weekly riders and see that relationship. Number of weekly riders are 100% linearly related to itself. And you'll see that for price per week and price per week, and monthly income of riders and monthly income of riders. What we're more interested in is how the other features relate to the number of weekly riders. So number of weekly riders are here. The price per week, we see that if the price goes up, the number of riders goes down. You see that indicated with this this negative number here. If the population of the city increases, and you also see an increase in riders, and so this is a positive correlation of 0.89. These are all pretty strong correlations. If we take the absolute value of these correlations, we can see that the price per week is the biggest at 0.96, followed by population of city at 0.89. So we're going to do our simple linear regression on the two features here. Price per week as the input feature and number of weekly riders as the output. And so we're going to go ahead and model. And the way we can model, I like it that when you go into Scikit-Learn and you look up linear model, they have the formula there for you, and they give you information about this package and what it does. The arguments that are in here, if you fit the intercept, that's true. Sometimes you can have it as false where you don't fit an intercept term. You can read a little bit more in the documentation. But today we're going to leave the default parameters as they are and just put in the information that we need. So it's going to fit the intercept and give us some different things. Also, what we'll get out of this, once we run this model, we can have access to some other attributes, like the coefficients. Those weights or numbers that are being multiplied with the input variable. In our case, it's going to be the price of the ticket, and what we're going to actually multiply that with, and then the intercept term, if we have one. And we're going to have an intercept term to see, we'll talk about that a little bit more once we calculate it, and give you different information about other items like ridge and lasso, elastic net, and we'll talk about those in different videos. So what I like about this is that they give you different methods too. So you want to fit the model, you can use we're going to use the prediction to predict using the linear model, and we can get parameters and different things. And what I like about this page is great because when you go all the way down, here they give you different examples. So here are examples using Scikit-Learn.linear model, linear regression, and we're going to use this one. When I come here, get more information still, and what I like the most is that thanks to Jacques Grobler, we have a code snippet that we can use for our modeling, and we're going to go ahead and take that. So copy it, and come back to our notebook, and let's go here. All right. I'm going to modify the code a little bit. We don't need the libraries and packages. We already have these up here, so we're going to get rid of that. And our x and y, we have to create an x and y. So our x is going to be equal to that price per week, which is what we have here. That's our price per week. And we have to have also, put the D up there, DF, and we also need our number of weekly riders here. Alright, this one says they split the data up manually. We're going to use the train test split feature to split the data up into training and test sets. So we're going to go X train, X test, Y train, Y test is equal to train test split. Uppercase X, lowercase y. Test size. Here we're going to choose 80% of our data to create the model, and so the test size is going to be 20%. We'll also have a random state or a random seed that we'll create, and that random seed allows us to have the same data to run the analysis on, because what happens whenever you use this train test split, it takes the data set and it shuffles it. It shuffles the data so that you make sure you have a good mix of records. Sometimes the records can come in and they could be sorted in a certain type of way. and where you might miss out on some of the variation that's lower in the data set if you just take the data set as is. So what train test split does is it automatically randomizes the data, and this random state 1, 2, 3 ensures that we get the same sample of data every time to sit down and run the analysis on to build the model. Okay, so we have our train test split. So now we're going to create the linear model, and this linear model, we don't need this part, this linear model part, because we already brought it in here, Scikit-Learn.linear model. So we just won't need to operate off of the linear regression part. So we're going to get rid of that piece there. So here we just need linear regression, just that. That's to instantiate the linear regression. And we're going to fit the model, regression.fit on our X data. We don't have a diabetes data set, so we're going to get rid of every instance of diabetes. Also, I noticed that we have the coefficients, so we can call in that regression.coef. And if we want our intercept term, which we do, we're going to also go back to the website and grab the attribute for the intercept. So this is the intercept. And I'm going to keep most of this code as is. And this is going to say intercept. And just as a reminder where we're going to get, where we're going to change this out, it's not going to be that. It's going to be intercept. So we go back into linear regression. I'm going to go back a page, and we're going to go to our parameters at the very top here. Past that, our attributes. So here's one, intercept, independent term in the linear model. That's the intercept, right? So we're going to keep that, copy that. I'm going to add that here. Okay. I think that should be good. Okay, so I think we're good here. Let's go ahead and run it. Alright, and these are our results. It says that our coefficient is -730. That means that, that's essentially our slope, and you can see that the line is going down. So this says that with one additional increase in the price per week for these tickets, the number of passengers will drop by 730. So you lose 730 passengers with every $1 increase per week. And this here, 197,000 plus, this says that this is our intercept. So this is what you get if you don't have a price at all. So if this price per week is $0, then you'd have this many folks who will be getting on the transmit and riding for free. So that's what we did here. We got a mean squared error. This becomes very important and useful when you want to compare different model fits. I like the coefficient of determination because you can quickly see whether or not the model looks good or not. It gives you 0.98. That's so close to 1. It's not, it just says that 98% of the variation in the number of passengers is explainable from this model. Right, so that's pretty good. Alright, and so we're going to use this model to predict an output from a new input or new information. Now we're going to say that $17 is the price per week. And if we charge $17 for a price per week for the transportation, how many passengers would we end up with? And so this shows that we have about 184,000 passengers, almost 185,000 passengers at a price per week of $17. Okay. And so yeah, that brings us to the end of our video. I hope that you liked the video. If you did, give it a thumbs up, like, subscribe. It's great motivation to keep me making these videos. I want to make sure that people are saying stuff that they can actually use. But yeah, so until next time, thanks again. Be well and peace.